Bonjour et bienvenue. I am Sébastien Gauthier and welcome to my channel, Sébastien 360. Today I will speak about image parallax, which in photography is the apparent movement of an object when photographed from different location. And if you are doing images for planetarium or any kind of full dome, VR or panoramic images, and you are using a multi-camera rig, you may have experienced parallax issue because in such a camera rig, every camera is not exactly at the same point. If you have an object too close to your camera, it may move in relationship to the distant background from image to image, and you may have hard time in post-production to obtain an error-free panoramic image. So to better understanding this phenomena and to characterize some of my camera rigs, I decided to write an equation about parallax and to make a Google Spreadsheet. And because this is useful to me from time to time, I decided to share this Google Spreadsheet with you. So you will find a link in the description where you can download a copy of this video. And I will present you how to use this and how you can put the dimension of your camera rig, the distance of your subject, and how my equation will give you the exact parallax error in pixel for your system. But just before we jump into this, I feel to push my luck and present you how I made the equation behind this spreadsheet. But I warn you, this is not for everybody. There will be a lot of mathematics and geometry in this demonstration. So if you feel that you are not in the mood for this, simply jump to this time code to be right at the spreadsheet. The equation goes like this. And by the way, I have absolutely no clue if somebody on Earth will be interested by this content and watching this video at the same time. So if you are such a person, please leave a comment down below. And of course, if you're not from Earth, feel free to leave a comment as well. This will really help my channel. Okay, so let's dive right into the math. My equation is based on a very simple model like this. So first you have your multi-camera rig. Here I have 3 cameras, but it can be any numbers of cameras as long as you have at least 2. Then you have your subject. It's what I call the object number 1 in the following sections. And it is this subject that will suffer from parallax issue when it will be the time to stitch the images together. And then finally in the model we have a second object which is far away. It can be a building, mountains, can be constellations in the sky, or anything that is far enough to be considered at infinity. And for the next section, we will need to measure the distance from the subject to the lens. And for that, the lens is considered to be at the entrance pupil. But if you don't know what is the entrance pupil, it's totally fine to just use the surface of the lens. So take your measurement from the center of the lens near the glass, and you will be fine. Now this is the exact same model, but represented in a more geometrical way. So we have our camera 1 and camera 2. We don't need other cameras because we only need 2 cameras to measure the parallax. So this is entrance pupil or lens 1, lens 2, and they are separated by a distance little d. And your object number 1 is right here, so in the center compared to these 2 lenses. And I have measured the distance from my first subject to the lens as D, capital D. And because it's in the middle, so it's capital D on the right side and capital D on the left side as well. So now if we are looking at object 1 from camera 1, this object will be seen in this direction for camera 1. And if we choose object number 2 in the exact same direction, on this sensor, the object 1 will be right in front of object 2. So they are on the same line. So now if we look at the object 1 from or seen from camera 2, the object 1 will be seen in this direction. But object 2 will still be in this direction, parallel to camera 1. Why it is parallel? Simply because object 2 is at infinity. And you know that anywhere you are, if you look at something at infinity, you will look at a parallel direction. So now the angle of parallax between the object 1 seen from these two cameras is this angle here. So from this camera, so as I said, both objects are parallel, but from this camera, both objects are separated by theta, which is the angle of parallax. So theta is here, it's also here, it's the same angle, and it's also at the top of our big triangle right here. For the next section, I will use only the yellow triangle, which is half theta here, half little d here, and the full capital D on the hypotenuse. Our yellow triangle is now rotated, but it's still the same triangle with the same dimensions. If we use trigonometry, we can find that by multiplying capital D by the sine of this angle, we can find the opposite side of the rectangle here. And by using the inverse sine function, the arcsinus, we can isolate theta. And theta is precisely the parallax angle for the difference of appearance for subject 1 in relationship to camera 1 and camera 2. But theta is expressed in an angle, it's in degrees, so it's not exactly in pixels yet, but this is what we will find in the next section. So for now on, we will consider that we have a fisheye lens that is projecting a circular image on a sensor. Now, your sensor might be smaller than your image circle. It may be bigger, but this is not important. The only thing you need to know is that we need to make the assumption that we have a polar equidistant fisheye lens. So the only thing you need to know about these lenses is that if you move an object in front of a polar equidistant lens, or you rotate an object around the lens, the image on the sensor will move for a certain amount of pixels. So let's say you move the object by 1 degree, and let's say that this produce a movement of 50 pixels on the sensor for the object. Because the lens is equidistant, every time you will move the object by 1 degree, you will have a shift of 50 pixels in this example on the sensor. And if you move by 2 degrees, it will be 100 pixels. 3 degrees, 150 pixels. But this is true only if you move the object on a trajectory that is crossing the center of the lens. And this is this property is very useful for our equation, because it will let us calculate a degree to pixel density in the lens. So all we need to do to measure that is to know the field of view on the lens anywhere where it's crossing the center. So often you will find in documentation for fisheye the diagonal field of view of the fisheye for your sensor. So in this case, I choose an example with 180 degrees of diagonal. So let's say we have a sensor of 6,000 by 4,000 pixels. So what is the number of pixels diagonally on such a sensor? We simply have to use the Pythagoras law right here, and we find that it's around 7,000 pixels. So because this is for 180 degree, if we divide those two numbers, we find that the density of pixel per degree on our fisheye lens is 40.1 pixel for every degree. So this is very interesting because now with this information, we know that if we make a full circle panorama with this camera or with this rig, we will end up with 360 times 40 pixels, which is 14,000 pixels. So this is a variable I call R, which is the total resolution for a full circle. And this is very interesting if you are making VR images, because in a VR image, your resolution is right there. So if you use a rig with a fisheye lens of 180 degree diagonally, with this sensor, you will end up with a VR map, a VR document of 14K, basically. So this is what R is about in a way. And now we have everything to measure to calculate the parallax in pixels. So it is simply R divided by 360, which bring us back to the pixel density per degree. So if you multiply that by your degree or your angle of parallax, you end up with your parallax in pixel. And because we found theta before, if we put the value, you have the full equation here. So let me present you an example, a numerical example of this. So imagine that you have this rig right here with 3 cameras, and they are both each separated by 20 centimeters, 0.2 meters. And you have a subject relatively close at 3 meters in front of the camera. So if we put all the numbers, and this is assuming that we have the same sensor and same lens as the previous example. So R is 14 something pixels divided by the 180. Here the distance between the lenses, 2 times distance between the subject and the lens, and you end up with a parallax for this rig, or I should say this subject in front of this rig, of 153 pixels. So this means that if you stitch your panorama from those 3 cameras and you obtain a perfectly aligned and stitched image at the infinity, it means that if you look at this subject that is not at infinity but at 3 meters, and if you look at the image with this camera, your object might be in front of a blue mountain, let's say, precisely at the center of a blue mountain. From this camera now, your subject might still be in front of the blue mountain, but it will be 153 pixels to the left of the mountain. So in relationship to the distant background, this subject will be shifted 153 pixels on each of these images. So this is what this equation is about. 153 is for the full resolution of your camera, but many times when we are making full dome films or VR films, we're not using the full resolution of the rig. Sometimes we scale it up, sometimes we scale it down. Imagine we are making a VR film and we need an 8K document. We need to deliver an 8K to our client, to our museum. So instead of using the full resolution of the camera right here, you just put 8K instead. And instead of obtaining 153 pixels of parallax, we will now have 87 pixels. So as you can see, the parallax is sensitive to the resolution of the total system. So the lower the resolution of your document, the less parallax issue you will have at the end. Note that this is for VR. If instead you want to calculate the parallax on your Dome Master planetarium film, and you have a 4K Dome Master, don't put 4K right here, put 8K. Why? Because the R variable in my equation is defined for a full 360 circle. So in VR, when they are talking about a 6K VR, as an example, they are talking about 6K along 360 degrees. But in planetarium, if we speak about a 4K Dome Master or 6K Dome Master. We're speaking for only 180 degree, only for the dome. So because of that, you need to double area number. So if you want 4K Dome Master Parallax, you need to put 8K in the equation. If you want 8K Dome Master, you need to put a 16K right here, and so on. Okay, we have now our Google Spreadsheet. If you would like to use it, simply go in the description below, click on the link, and you will have your own copy of this document to use with your Google account. So we have first the distance between the lenses in our rig. So let's use 0.2 meters. And let's say we want to know the parallax for a subject that is located 3 meters away in front of our rig, or more precisely in front of a lens. And by the way, about the measurement units, you can put anything you want there. It can be millimeters, inches, light years, anything you want, as long as you use the same units for the distance between lenses. Let's say you use millimeter, you must then use millimeters for the distance of your subject. And that's it. As long as you have the size of your camera rig and the distance of your subject, you are able to calculate the parallax error for any given document, either VR or Dome Master. So let's say we have a Dome Master of 4K. So this subject in front of this rig will produce 87 pixels of parallax along the meridian. And if you are interested by VR, let's say 8K, you have now 87 pixels of parallax along the horizon using this rig. And on the right here, you have a graph showing you the error for a range of distance. So not only 3 meters, but in this case, it's from 0 to 50 meters, and you can change the range. And this is useful if you want to have an idea of the danger zone of your rig. So as you can see, when you are far away, 40 meters, 3 meters away, there is not much parallax. But when you reach, let's say, 10 meters or closer, the parallax start to increase, and this is expected. The closer you are to your multi-camera rig, the worse it will be in terms of parallax. But I would say that for this system, the true red zone is below 3 meters, because there the parallax will increase very, very abruptly. So if you are to photograph a subject 3 meters away in front of this rig, you should have a huge overlapping between your cameras to be sure that you will be able to fix this parallax in post. We can also, with the spreadsheet, know the exact parallax error on the sensor at the native resolution of your camera. To know this, we need first to fill these two boxes here. So you need the field of view of your fisheye lens. So let's say I have a 180 degree diagonal, and I'm using a sensor that has diagonally 7,211 pixels. So this is to match the example in my mathematical demonstration. And I will be brief about this section here, but if you have more detail on how to use this section, please go back to the mathematical description. Now we have not only the parallax for an 8K VR, but we also know the native parallax on the sensor of the camera. And you also know now that the maximum resolution of this rig, or the native resolution of this rig for a full 360 circle, is 14K. So if you are to make a VR document using this rig, you will have a 14K document. And if you are to make a full dome film with this rig, you will have half of this, so around 7K. Why it's half? Because in VR, this number, it's for 360 degrees, and with the dome, we are only using half of the full circle, so 180 degrees. In the video description, you will also find a link to an image folder where I share the result of an experiment to test the validity of my equation. I took a series of pictures while varying the subject distance and the distance between the lenses of my rig. And you can find those distances in the file name of the images. And you will also find the field of view. I have loaded all the images in Photoshop, and as you can see, it's a series of test images with this vertical subject at different locations. And let me now show you the last two. If I flip between the two images, you see that there is a parallax. But if you look in the distance, you will see that these images are not aligned. So I will put the first one, the top one, with 50% of transparency, and I will move. Let me zoom even further. So I will move the image to make sure that they are aligned together. So now if I flip the image at infinity, or at least far in the distance, both images are converging, but the closer we look, the bigger is the parallax issue. Now the question, does this is in tune with my equation? We know from the file title that the lenses are separated by 406 millimeters. So let me put this in my spreadsheet. So 406 millimeters, and the distance of the subject is 7620 millimeters, and the field of view, the horizontal field of view, is 36 degrees, and the image size is vertically is 2048 pixels. So 2048. So according to my equation, we should have 174 pixels of parallax. So let's have a look. So we'll use a guide to the right side of this orange line right here. Okay, and for the other image, the right side again. And I will use just this rectangular marquee to measure. So it's 174 pixels. So exactly what was predicted by my model. As you can see, this equation and this spreadsheet is working pretty well, and it can be very useful if you know how to use it. Of course, maybe I was lucky with my my example. It won't always be accurate to the pixel, because in my test I also made a very precise measurement of the field of view of the lens, and I calibrate all the images, but nevertheless, it will give you a very good idea on the field with your own camera rig. That's it, my friends. I hope you enjoyed this video and the Parallax spreadsheet. About this video, this is my very first on my channel, and it happens to be very technical and very advanced, I would say. But I promise that not all my videos will be like this. My goal is to speak about planetarium stuff, but also to speak about immersive filmmaking in general for Fulldome and for VR. So if you are interested by this subject, please subscribe to my channel. So until next time, take care. Au revoir. À la prochaine. Yeah.